The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
What is this? I'm impressed. Good morning. I'm not Don Sadaway, as you can tell. He's at a conference. I'm not sure. I think it's in Halifax. No, what the heck can you have in Halifax? Education. Okay. A couple of announcements. The obvious. The first test is Wednesday. Maybe not so obvious, but it's posted on the website. There'll be a review session for those of you who care to come, given by myself in 26100 tomorrow night, starting at 7 p.m., going until the last question is answered. That's why the infinity. Please don't show up at 10:30 or 11 and start asking questions. I just flew in from Beijing. For those of you who don't realize it, it's now about 12 o'clock in the evening tomorrow in Beijing. Yeah. So anyway, I'll probably fall asleep by about 10:30. Anyway, okay. One little thing about the quiz. Professor Sadaway always gives some admonitions about how to take these quizzes, and one thing that I'd like to add to it, and that is, and I've told this to my recitation sections, that when you do these quizzes, in spite of the fact that it might be trivial in some cases, make sure you carry the units through. If you've got a problem that has units associated with it, do the exercise of carrying the units through. Because guess what? If the units are supposed to come out in meters per second, and you get seconds per meter, what do you figure the chances of that problem being right are? 0. All right? If the units come out in meters per second, you'll quickly discover that the problems in 3091 are just not that complicated. And so even by units analysis, if the units come out right, you got a good shot that unless you've really, really messed up, that the answer is going to be right. The second thing is ballpark it. That is to say, guess the answer ahead of time. Strip all the decimal places off. Just don't go with powers of 10, and then sing what the answer should be. And you'll be within 25 or 30% every time. And that's a good thing to know, because if you come out with an answer that's somewhere near the diameter of the universe and it's supposed to be the diameter of an atom, then you'll know that you probably made a mistake. So those are two pieces of advice. Okay, last day you talked about the Born-Haber cycle, an octet stability via electron transfer. The Born-Haber cycle was designed to allow us to calculate the energetics of, in particular, the ionic bond. And the thing we need to remember are a couple of things at least, and that is that the lattice energy, as is depicted by the Madelin constant, is dominant. And that the Madelin constant, what does it represent? It's a geometric factor that's unique for each crystal structure. So that's something you go and look up. So you go and look that up, and those are the key things. And as a result of that, the achieving of octet stability by electron transfer, we tumbled to the idea of an ionic bond. An ionic bond where one atom donates an electron completely to the other atom, sort of like servanthood. One donates yourself completely to another. Okay, so that's where we are. But we got a few problems. Okay, sodium chloride works, magnesium chloride works, magnesium oxide works, all of these from the group 1 and 2 to the group 5 and 6 elements. But what about elements, what about molecules like hydrogen or nitrogen or maybe oxygen, or we can keep on going, chlorine, all right? We know these are stable. And if we wanted to try to fit, say, hydrogen into this scheme that we have, we'd have to do what? We'd have to figure out a way to achieve octet stability by electron transfer. Well, we've got two hydrogen atoms here, and well, what would have to happen? Well, we'd have to have one of these hydrogen atoms go to an H plus an electron, right? So now we have a hydrogen ion here, but at the same time, another hydrogen would have to do that. And clearly, we can't do both. This one here is what? Hydrogen with an added electron. That's isoelectronic with helium. This thing here, this is just a naked proton. So it doesn't work. It doesn't work. So we need to find another scheme, and that solution was provided for us by G.N. Lewis. Right? G.N. Lewis. And he asked the question, what if we could share electrons? And by now I'm meaning the valence electrons. All right? What if we could share electrons? Well, let's look at hydrogen and see what would happen. Well, we know that hydrogen is 1s, right? So if we take another hydrogen, we stick it over here, 1s, we know we have an electron here, and let's say the X denotes the electron from this hydrogen, and now we form a bond. And what do we have? Well, this is isoelectronic with helium, right? And so is this isoelectronic with helium. And so we think we have each hydrogen has access to each electron, and now we have a satisfied system. Now we could do the same thing with, well, we're going to do it with nitrogen in a minute, but this is a case where we have two atoms sharing electrons. And in general, what we have is sharing two sharing to achieve octet stability. Let's take a look at nitrogen to see if it goes to see if it applies there as well. Well, we know nitrogen has what? Nitrogen is 1s2, 2s2, 2p3. So we've got 5 electrons here in the valence shell. If we take nitrogen, we've got N2, and let's just, we go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. All right? 1, 2, 3, 4, 5, 6, 7, 8. Here we go. We've got two cases where each one of those things now is isoelectric with neon. And we have achieved octet stability in the same way. All right? So Lewis called this, he called it cooperative use of valence electrons. All right, so you take the co here, and we take the valence here, and out of that comes covalent. All right? Covalent. All right? And let's be a little, now we need to put a little terminology here. This region in here contained the bonding domains, right? And the non-bonding electrons are non-bonding domains. And this structure that I've depicted here using the X's and O's is called the Lewis structure. Right? It's called the Lewis structure. And let's see. This is actually from Lewis's notes. Now remember, this is 1902, so there wasn't a whole lot going on. There was a lot of physics going on, but we didn't know a whole lot about atomic structure back in those days. But you can see this is right out of his notebook, and you can see he's arranged the atoms by row, and he's trying to figure out. See, lithium has 1, beryllium, magnesium have 2, boron, aluminum have 3, and he's trying to figure out how to arrange these things. This is right out of his notebook. And look up at the top here. He's got a bit of a mistake. He's trying to make helium octet stable. He's trying to put 8 electrons around helium, and it ain't working. Right? But look down here. He's got a box within a box. This is 1902. This is reminiscent of what? The shell structure, which people hadn't even thought of. So this is in his notes. He didn't publish these notes, and he didn't publish anything related to the Lewis structure until about 1912 or 1913. But you can see that he was thinking about this structure for all along. Whoops, let's see if I can get this to... Let's see. Okay. Now, this is a more formal look at that structure, and you can see what he's done. This is I don't know what the date's in, 1916, excuse me. It's at 1916, and you can see what he's done. He's taken the elements and he's arranged them, and he's stripped off all of the non-valence electrons, and all he's done is leave the valence electrons associated with. So you can see the alkali metals here, lithium, 1 electron, and then beryllium, magnesium, 2 electrons, all the way over here to neon and argon, where you have stability. There's fluorine and chlorine, where you have 7 electrons. So that's his gift to us, the Lewis structure, and the idea that you could share electrons and form a covalent bond. Now we need to go a little bit further to put some more meat on this thing, because we haven't quantified it yet. We've got the concept, but we haven't quantified it yet. But let's take a look and see about water. These are so-called homopolar molecules. The atoms are the same in each one. And let's try one with two different atoms. Let's take a look at water. We know that hydrogen is 1s1, and oxygen is 1s2 2p. Whoops. S2 2p4. So there's 6 electrons in the valence shell. And let's try oxygen. Well, oxygen, we'll put a hydrogen here, and 1, 2, 3, 4. We've got to put 6 electrons around it, so let's put 1 here and 1 here. We've got an electron from each of the hydrogens, so let's put that here, and that's there, and that works. So now we have what? We have 2, well, let me draw this as a square. We have 2 bonding domains, right? 2 bonding domains, and we have 2 non-bonding domains. Now, we know that there's more structure to this molecule. Water is a very unique molecule. It's one of the only compounds, there's only, I think, 3, where the density actually goes down when it freezes. Think about that. Think of anything else where the density goes down when it freezes, and think about where we would be if that wasn't the case. Ponds would freeze from the bottom up. That would be a bummer. All the fish would freeze in the wintertime. Water has some pretty unique properties, which we'll deal with a little bit later, but it all relates to the bonding. All relates to the bonding. Okay. And now Lewis actually listed some rules, and what we want to do is go by example here. All right? And these, by the way, are called Lewis structures. Lewis structures. All right? And so he came up with a set of rules, and let's take an example and see how these apply. And as an example, let's take sulfuryl chloride, SO2, make it a little complicated, Cl2. All right, so don't worry about these compounds, and we'll tell you all you need to know if we have, except for how to draw them. And it says, okay, center the element with the lowest average valence electron energy. Well, if you look in your sulfur is less than chlorine, which is less than oxygen. So sulfur has the lowest average valence electron energy. So that says put the sulfur in the center. All right? All right? So put the sulfur in the center. Then it says count all the valence electrons. Well, sulfur has 6. That's 3s2, 3p4. Oxygen, 2 times oxygen. That's 12, because sulfur is 2s2, 2p4. And chlorine, there's 2 of those. That gives us 14. And that's 3s2, 3p5. And so we got to come up with, we have 32 electrons that we have to use. Okay. Then it says, draw a single bond from each surrounding atom to the central atom and subtract 2 valence electrons. Okay. And let's just put chlorine here, oxygen here, oxygen here. So 2, 4, 6, 8 minus 8, that gives us 24. So we have 24 electrons that we have to come up with. And then it says, okay, distribute the remaining electrons in pairs so that each atom has 8. Place the non-bonding pairs on peripheral atoms first, which the higher average valence electron energy. All right, well, oxygen has the highest valence electron energy. So let's go and put the 1, 2, 3, 4, 5, 6 here. Let's do 1, 2, 3, 4, 5, 6 here. And okay. And let's put the atoms around. Now we'll do the chlorines. Chlorines have 7, right? So 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. Okay, so now we've got taken an electron from that sulfur, put it here. An electron from that sulfur, put it here. So how many we got in the sulfur? We got 1, 2, 3, 4, 5, 6, 7. Well, son of a gun. 1, 2, 3, 4, 5, 6. Sulfur, 1, 2, 6. We got 6. We've used all the electrons. But what do we have here? Well, this chlorine has taken 1 electron from the sulfur, but the oxygen has taken 2 electrons from the sulfur. This is a kind of a special, and you might expect that. Oxygen has the highest average valence electron energy. So it's going to want to scarf and take these electrons. This is called a dative I bond. It's what it's called when an atom takes both electrons in the bond. All right? So what do we have? We have 1, 2, we have 1, 2, 4 bonding. Bonding domains. And how many non-bonding? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 non-bonding non-bonding domains. Okay, so this is looking pretty good. We've got octet stability. We've got each one has an inert electronic structure. But a few things to note. We know that because the sulfur and the chlorine and the oxygen have different average valence electron energies, they'll have different electron affinities. So this bond is going to be a little bit different than this bond. We have to account for that in some way because we know they don't have identical average valence electron energies. Okay. Let's start over here. Whoops. Okay, let's try another one. Let's try something like 4, which is what? Methane. Methane. What do we know about methane? Well, we know it's stable, but we also know that it's symmetric. Right? It's symmetric. We know that it's nonpolar. All right, so those are the things that we know about it. We also know that carbon is 1s2, 2s2, 2p2, and we know what hydrogen is. And so if we look at our box notation, right? We've got 3 states in the p orbital. We've got 1 in the s orbital. If we apply the Hund rule, we've got up arrow, down arrow, right? But there's something else that we know, right? We somehow have to take hydrogen, attach it to carbon, and we have to make it symmetric, and we have to make it nonpolar. And yet we know that the shape of the s orbitals is spherical. The shape of the p orbitals is, however, not spherical, is it? It's asymmetric. And moreover, they're at right angles to one another. That we've learned. So somehow we have to figure out a way to take orbitals that are non-symmetric and convert them into orbitals that are symmetric. Now, what does that mean? If it's symmetric, that means that each bond has exactly the same energy. Same bond, symmetric bonds means equal energy, which means equal lengths. If we can do that, we'll end up with a symmetric nonpolar molecule. Well, this stumped people for a while until another fellow came along, Linus Pauling. He's famous for a lot of things, one of which is covalent bonding. And he said, well, let me take a look at this. What if I were able to mix the orbitals? All right? What if I were able to mix these orbitals and produce what he called hybrid bonds? Right? Hybrid bonds. And how would he do that? Well, this is where the thinking came in. He said, let's just mix the 2s and the 2p orbitals. Right? 2s, 2p orbitals. And I know I need to come up with 4 symmetric, equi-length bonds. And, well, let's just see. Let's draw the structure here. And so I take and I mix the 2s and the 2p's, and by my Hund rule, if I can come up with 4, I've got, what have I got? I've got 2 states here, 3 states here, 2 here, I need 4. And if I can come up with these bonds, 4, by the Hund rule, I fill them like this, and there I have it. I have 4 bonds that are of equal energy, and he called this SP3, an SP3 hybrid, right? An SP3 hybrid. And now I can't do the drawing justice. But let's take a look at how we do this. This is the graph to the left. This is the s orbital, symmetric. These are the p orbitals. And these are what? These are the probability densities, right? Our friend Schrödinger told us that this is what if you solve for the wave function, this is what the probability densities look like. If I now hybridize these, if I take these and I make 4 symmetric, now these are just the SP3 orbitals. The hydrogen's not on there yet. Notice this the orbital looks kind of funny. It's got a big lobe and a little lobe, and they're sort of backed into it. So this forms a tetrahedron, which forms the SP3 hybrid orbitals. Now, the hydrogen, on the other hand, the hydrogen has symmetric s orbitals, and now we take, and this is just another way to look at, another way to look at it. You take these SP3 hybridized orbitals, and you add a hydrogen to each one, and now what do you have? You have a symmetric molecule, and let's see. Whoops. You have a molecule where we put the carbon in the center, and we go up like this, and out the back, and now you have a tetrahedron with equal length bonds, and it's going to be symmetric. Now, will it be polar or nonpolar? We're getting a little ahead of ourselves. What makes something polar versus nonpolar? Well, if this bond has completely identically equal sharing of electrons, then this bond will be nonpolar. However, we're going to see that that's not the case for hydrogen and carbon. This bond will be nonpolar. So that means we got 1, 2, 3, 4 nonpolar bonds in here, and yet the molecule is symmetric and nonpolar. What's going on? Well, what's going on is the carbon is at the exact center of the tetrahedron, so the nonpolar bonds cancel each other out. The two sources of charge cancel each other out, and you get a nonpolar molecule. Okay, so that's what Pauling did. But he did a little bit better. Lewis, by the way, didn't get a Nobel Prize, but Pauling did get a Nobel Prize. So you say to yourself, well, Lewis is the guy that came up with the idea. Why didn't he get the Nobel Prize? Well, he came up with the theory, but he didn't reduce it to something quantitative. Pauling did that. And so let's go back and take a look at the energetics again. Let's take another look at the energetics. Now, last day we looked at the energetics of the ionic bond, right? And we wrote something that looks the energy is equal to minus the Madelin constant times Avogadro's number Q1 Q2 over 4 pi epsilon 0 R0, and we knew that if we know the crystal structure, we can get the Madelin constant, not a problem. And what we need to do is to get this. Well, how do we get that? Well, if we just take, for example, MgO, and let's try Mg magnesium chloride, just as an example. We can put the magnesium 2 plus here, and then we put the oxygen here, O2 minus, and we know that this gives us our R0, right? So we can go and measure that. We haven't said much about how to measure it, but you can measure it. If we wanted to get the chlorine, we could just put the chlorine over here, and we'd measure another another radius there. And we could easily calculate the energies. Well, with covalent bonding, it's not so simple. All right? It's not so simple. And so let's see how. Let's take an example. And let's take an example, HF, hydrofluoric acid. All right? Well, if we wanted to draw that, we have HF. Whoops. It would look something like that. But let's say we wanted to calculate the energy. Now, Pauling was trying to figure out how to do this. And he said, well, what if I were to take and just somehow add up bonds, for the energies of bonds, or derive this energy from energies that I do know. All right? And so let's take the HH bond. More particularly, the HH bond. All right? And let's ask what the energy of that is. Well, we can look that up, and that's table in your text, by the way, B14 in your text. All right? And we can come up with a number of 435 kilojoules per mole. All right? 435. Well, if we want to get HF, let's see what the FF bond is. Well, you go look in your table and you come up with 160 kilojoules per mole. So if I had to guess, what would you guess the bond energy would be in HF? Well, 435, 160, take 435, add it to 160, divide by 2, maybe that would be a guess. Or I could come up with some other scheme, but you would kind of guess that it would be somewhere in between. Right? It would be somewhere in between. Well, what's the actual value? Well, the HF bond energy is actually 569 kilojoules per mole. So we have a problem. The problem is we can't add these two together. We can't come. There's no way that we can get from here to here to here without knowing a little bit more information. And well, we get that information by going back to the definition. What's the definition of a covalent bond? Sharing of electrons. Well, they don't have to share equally, do they? And if they don't share equally, then the individual bonds might have different energies. And so that's exactly what Pauling proposed, right? And he actually proposed sharing unequal sharing of electrons. And what did he use for a he needed to get quantitative, and he defined a term called the electronegativity. And in your text, it's E sub n. But in most chemistry texts, it's also chi. That's the more common term. And it represents the ability of an atom to attract electrons in a bond. All right? The ability of an atom to attract electrons, and in particular in a covalent bond. All right? And he came up with a scheme, and this is how he ranked things. And you can see a parallel. If you take a look at last day or the day before, you'll see that we talked about average valence electron energy. There's a striking parallel here, in that the group 1 elements have a tendency to want to give up electrons, whereas the fluorine, chlorine, and those and bromine have a tendency to attract electrons. And so this is a schematic of the electronegativity scale. Now, Pauling originally assumed that fluorine was the most electronegative element. So he referenced or normalized everything to fluorine. Since that time, we've been able to actually measure these bond strengths by PES, photoelectron spectroscopy. And when you do that, it turns out that fluorine doesn't come out to exactly 4. And this is a figure out of your text, and you can see that fluorine, instead of 4, it's about 4.19. But it's as you would expect. The most electronegative elements, fluorine, chlorine, oxygen, are over here. The highest one is neon, but the lowest one is way down here, cesium. And you would expect that the group 1, absent hydrogen, would be the ones that would have the least. Now remember, the formation of the ionic bonds was from group 1 and group 2, and over here with group 6 and 7. So those are the ones that are most likely to form ionic bonds. Okay, not only did he propose it, he quantified it, and he did something even better. Let's see. He defined something called, how much time do we have? Partial charge. Right? Now this is what got him the Nobel Prize. And he defined partial charge, and I'll give you the formula. G sub x, this is in your text. N sub x in an XY bond, right? Chi sub x plus chi sub y, right? Where G sub x is the group number, right? N sub x is the number of non-bonding electrons, and B sub x is the number of bonding electrons. Okay, now let's take this and look at what we get if we try HF. All right, we know this is what it comes out to. This is H. Wait, we got one X here. We know that this is going to be, by measurement, this is going to be plus and this is going to be minus. It's going to be a dipole. This is plus, this is minus. And we know that chi of the fluorine is 4.19, and chi of the hydrogen is equal to 2.30. Okay, well, if you plug that in, let me just do one of them. Just do the fluorine, and by the way, if you do this for the hydrogen, it ought to come out the same. That's equal to 7 minus 6 minus 2 times 4.19 over 4.19 plus 2.3, and that gives you a number for the fluorine minus 0.29. All right. Now, if you do the same for the hydrogen, you'll come out with the same number, but it'll be plus. All right. But it'll be plus. And so then what that tells us is HF is polar. HF is polar. Okay, so we did that, and now let's go back to. Whoops, I'm running out of space. Let's go back to methane, and see what happens. See what happens there. Let's go back to methane. Well, the chi of the carbon is equal to 2.54. Chi of the hydrogen, again, is what? 2.3. And so what this tells us, since these aren't equal, that tells us that the carbon-hydrogen bond is not, well, better way to look at it, is polar. Right? Hydrogen bond is polar. And so if we go and we draw this again, if this is the carbon here, hydrogen, 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 hydrogen like this, then this is going to be a little bit plus, right? A little, whoops, plus, and this end is going to be negative, all right? So we know from our calculation that we can do over here that this bond is polar, right? This bond is polar, but again, as I alluded to earlier, because the carbon is centered in the tetrahedron, because of the SP3 hybridization, the molecule itself is symmetric and nonpolar. Okay? And for this, he got a Nobel in, I think, 1954. 1954. Okay. Now, one last thing that he did is that he said, okay, what's going on here? Well, on the one hand, we have ionic bonding where we have complete sharing. On the other hand, if we have a perfect covalence bond, we have identical equal sharing. But we know that just by this calculation that we don't have equal sharing. So somewhere in between, the bonds are, we have a range of bonds between ionic on the one hand and perfectly covalent on the other hand, but there's a whole range in between. So what's going on there? Well, Pauling also suggested that for that case, that the bonds are partially ionic and partially covalent. And he came up with a relationship to calculate the percent ionic character, all right? And I'll just give it to you. This is a squared. To give you a percent. All right, so this is a relationship, and so you can see where chi comes in here. And this is the difference in electronegativity between the two elements. All right? Let's see how much time. Okay. He also, let me see. He also, lastly, to close this out, he also developed an analytical expression for the energy of that covalent bond, which is really what we want. All right? So the type of bond energies that we can go and look up in tables are individual atom bonds, HH, FF, and the like. But he said the energy of an XY bond is going to be equal to the square root. It says, right? So the XX bond and the YY bond, we can look up those energies, plus 96.3 delta chi squared in the kilojoules per mole. Where's the 96.3 come from? Well, it's a conversion factor. So this gives you the energy of the bond. Now, if we plug in the numbers, for HF. What do we get? Well, we get square root of 435 times 160 plus 96.3 times IH minus chi carbon, squared. And you get, this number here is 2.3, this is 4.19. You get the E of the HF is equal to 608. Okay, now where's my other one? Somewhere here, 569 over here, kilojoules per mole, and by his formula, he gets 608, which isn't bad, which really isn't bad at all. Okay, so what we've gone through today is we've introduced covalent bonding, and we've figured out a way to quantify it. Not only did we figure out a way did we describe how we quantify it, but we've also quantified how we tell the difference between covalent and ionic and percent ionic character. So those are the key things to remember for today. But hold on a minute. What have we got? Got a few minutes here. Let's give you an example of SP3 hybridization. There's a scientist, Thomas Midgley, and Professor Sadoway calls him SP3 Midgley. He developed a whole lot of compounds based on SP3 hybridization. And this one here, some of you might recognize, is dichloro-difluoromethane. It's also known as a CFC. And this is the shape. It's SP3 hybridized. Now, it's not going to be symmetric, is it? Because there's 2 fluorines and 2 chlorines, so it's a non-symmetric molecule. But what is good about what is so unusual about this? Well, up until probably 10 years ago, this was the primary propellant in just about every kind of spray thing that we had, hairspray, everything. It's called Freon. It's also used in air conditioners. What was neat about it is before that time, the predominant species to use for air conditioning or refrigeration was ammonia. And not too many people, actually, if you talk to your grandmother or grandfather, there were some refrigerators that were actually made that used ammonia. But when they sprung a leak, you had a problem. And so by and large, until these Freon was invented by Midgley, there wasn't a good gas that had the right properties to be used for a refrigerant. And so this was good as a refrigerant. But something else can happen with these things. And I think this is, you hear about this in the news a lot. If you get some of these in the upper atmosphere, this a photon, an ultraviolet photon, has an energy capable of breaking this bond. When it breaks this bond, that chlorine atom, a free chlorine atom, comes down and reacts with this is ozone, with the ozone in the upper atmosphere, and you end up with the destruction of the ozone layer. And this is what you hear a lot about in the news, Kyoto and all this kind of thing about destruction of the ozone layer. Well, this Mario Molina, who's a faculty member here at MIT, won a Nobel Prize for describing this this process. He wasn't here at MIT when he won the prize, but here's the paper, the actual paper. Now, you think you can make a mistake on your exam? Take a look at this up here and tell me what that all is. I have no idea. That's exactly the actual paper. It actually should be chlorine catalyzed, shouldn't it? But who cares? He got the Nobel Prize, and I'm sure he's not worried about it at all. Okay, good luck on your test, and remember the review session if you care.